All right, problem 3 in group theory. Let G be an abelian group having elements of orders 8 and 18. Prove that G has an element of order 72. Okay. Begin proof. Let G be an abelian group having elements x and y in G such that the order of x is 8 and the order of y is 18. Okay, and a standard fact about elements from any group, or potentially a finite group, or potentially any group actually, potentially, I don't think finite actually, is that we have remark that, let's see, the order of any element from a group to some power is equal to, it's the order of that element divided by the GCD of the order of that element and the power. Yes. Remark that for, so let's see, for G in G and K in the naturals. Maybe I should have put a period there. Remark that for G and G and K in the naturals, we have this guy. Yes, and from this we can say, hence, if we look at y specifically, hence the order of y squared is equal to, it's the order of y, which we know is 18, over the GCD of 2 and 18, which is 2. So 18 divided by 2 is certainly 9. Okay, and then I'm going to make a claim. We claim that if G is abelian and G and H are in G such that the orders of G and H, such that the orders of G and H are relatively prime, then the order of the product is equal to the product of the orders. Which looks about right, and this is particularly useful to this problem because we have an element of order 8 and an element of order 9, hence the element of order x, the element x times y squared is going to have order 8 times 9, since 8 and 9 are relatively prime, which is 72, which is what we want to prove. So if we prove this claim, we combine it with this fact, we have our claim. We have an element of order 72. Okay, so we want to prove this claim. Okay, and we have that the abelianness in G is just going to let us do whatever we want with exponents, pretty much. Okay, so we want to let the order of G equal n and the order of H equal m, such that n and m are relatively prime. Okay, so many typos. Okay, maybe I should say to that end, let, but whatever. Okay, and how can we proceed? Okay, so we want to show that the order of GH divides NM, and NM divides any order of GH, essentially. So we'll do the first half, that's not that bad. How should we say this? Let's think about that. Maybe notice that if we take GH and we raise it to the nmth power, whoops, it should be that. Well, because we have abelianness, we can say this is just equal to, I'm going to put it in parentheses, G to the n to the m times H, put it in parentheses, H to the m to the n. I mean, we can rearrange stuff however we want, essentially, with exponents because of abelianness, which is nice. And then from how we defined their orders, this is just the identity. It's just the identity. Okay, so we showed that GH raised to the NM is equal to the identity. Hence, the order of GH divides NM, or it's less than or equal to NM, same thing. Whatever categorization you like. Okay, and now we want to show the opposite. NM divides any order of GH. So if k is any possible smaller order of gh, so if k is any, maybe I should say any other possible smaller order of gh, oops, I just went to a completely different problem. Oh, I did it twice in a row. Okay, then let's see, we have gh to the k equaling the identity. So we have that gh to the k, and I'm just going to pick, one of my letters, either g, either n or m, doesn't matter, just to exhibit the fact that, okay, we can, well, first of all, gh to the k, if we were to just look at that part, that's certainly the identity. And then the identity is the mth power is the identity, so this is certainly equals the identity. And on the other hand, if we were to distribute that km power, I guess, let's see, we'd get that. And again, we can flip it however we want, so maybe I'll put the m first, and maybe, yeah, I'll even be explicit like this, like I did previously. Okay. And we'll compile that so I can look at it. Okay, we know that h to the m, because the order of h is m, is just the identity. So this gives me g to the km. Okay, so what are we saying in this line? We're saying that g to the km is equal to the identity. Thus, the order of g divides km. And I'm not going to write the order of g. I think it's more useful to look at n. So we have n divides km. And similarly, we can use the same logic, but switch m with n. Similarly, we can show that m divides kn. Okay, so we have n divides km and m divides kn. Since n and m are relatively prime, we have that nm divides k, and m divides k. Because n divides k times m, but n can't divide m, and m divides kn, but again, m doesn't divide n because they're relatively prime, so n times m has to divide k. Okay, and now we've showed it divides both ways. The order of gh divides nm, and nm divides any other possible order of gh. Therefore, the order of gh is equal to nm, which is the order of g times the order of h. So maybe I'll write that so it's explicit. Okay, so we have our claim. Now we can observe that since 8 and 9 are relatively prime, we have that the order of xy squared is equal to the order of x times the order of y squared, which is equal to 8 times 9, which is 72. As desired. Okay, I don't like how that cuts off, so why not? We'll throw it in a bigger thing. So this is an element of order 72 in G, because of closure and stuff. So we finished part A, which again I should label as part A, and all that remains is part B, which I'll do in another proof environment, why not? B, how do I capitalize that? Okay, B says, show by example that G need not have an element of order 8 times 18 equals 144. All right, we'll consider, we want an abelian group, so we'll consider Z8 direct summed with Z18. And we'll notice that 1, 0 and 0, 1 have orders 8 and 18 respectively. Okay. However, if xy is, again, I shouldn't use the same variables, but whatever. If xy is some arbitrary element from this direct sum, then, well, if we multiply by the least common multiple of 8 and 18, that'll definitely give us 0. Then, which 72 is the least common multiple. 72 times xy is equal to 72x, 72y, which is equal to 0, 0. The identity, and again, cut off, so I'm going to just put that in there. Hence, we have that the order of an arbitrary element in this abelian group is less than or equal to 72. So it certainly doesn't have an element of order 144, which is greater. And that's the entirety of 3. Pretty cool proofs.